Welcome to our lesson on the normal distribution fundamentals. Up till now, we've only talked about one other distribution. It's called the binomial distribution. We just finished talking about it. And the binomial distribution models situations with a fixed number of trials and two possible outcomes. That was our success or our failure. And this is great for understanding real life examples such as whether a customer makes a purchase or not. But all of these examples with the binomial distribution are examples of variables that are discrete, where the possible values that x can take on are counted. But now we're going to shift gears and talk about a distribution that is continuous. And this is one of the most widely important concepts used in statistics. It's called the normal distribution. And again, unlike the binomial distribution, the normal distribution models continuous variables, and those can take on any value within a given range, such as height or temperature, weight or time. These values are not limited to whole numbers for the variable. So let's start by looking at the properties of the normal distribution. The normal distribution is a continuous probability distribution that is symmetric about the mean with a bell-shaped curve. It is characterized by the mean and the standard deviation. So what do we mean by symmetric about the mean? It means that if you look at the center where the mean is, and you imagine that there's a mirror there, it's going to look the same on either side. So properties of the normal distribution that are very important. The total area under the curve represents the probability, and it should add up to 1 or 100% because that's the total amount of the area under the graph should be the total amount of the probability. The area over the interval represents the probability that the variable falls within that interval. The distribution is symmetric about the mean. We just mentioned that, but it's very important because we can use the symmetry to answer probability questions, which we're going to get into here in a minute. The mean, median, and mode are all going to be equal. In the case where we have a normal distribution, because the graph is symmetric, it's not skewed in either right or left, it's not bimodal, it's symmetric, it has one peak in the middle, so all of the averages are going to fall right in the center and they're going to be the same. Now it looks like here that the tails touch the graph, but theoretically the tails never touch the x-axis. So I want you to picture when those tails come down, it's going to get closer and closer and closer to the x-axis, but it's never, theoretically, never going to actually touch the x-axis. And that's based on the formula for the distribution function. Now, something that is also very important, there's something called an inflection point, and this is where the curve changes concavity and is approximately 1 standard deviation out from the mean. So let me explain what that means. When you have something that's concave up, it has kind of a bowl shape. This is concave up. When you have something that's concave down, it's going to look like an upside down bowl. And when the shape of the graph changes from concave up to concave down, that's called an inflection point. So when we look at our normal curve here, this part of the graph right here is concave down. Let me change colors. When you look at the rest of the graph, it starts to turn concave up. So it looks like a bowl facing up. Now at that point where it changes from concave down to concave up, that is where you're going to have your 1 standard deviation that's going to come out from the center. So whatever the standard deviation is, here's the mean. you're going to come out 1 standard deviation. That's going to be where the inflection point is. Now let's look at the normal distribution notation. As a quick refresher, for the binomial, it looks like this. We have x with our tilde, and then we have our b, and then we have inside the parentheses whatever the values of n and p is. And that helps us describe the distribution. For the normal distribution, we use an n for normal, and then the values that shape the graph that is important to know that we need to define in here is the mean and the standard deviation. So here's an example. This notation where it says x with the tilde and then n 165.6, this says that x is normally distributed with a mean of 165 and a standard deviation of 6. So let's practice this notation. So in example 1, it says the amount of snowfall at Mount Monadnock in New Hampshire during the winter months is normally distributed. Let x represent the total snowfall in inches for winter season. On average, Mount Monadnock receives 85 inches of snowfall with a standard deviation of 12 inches. Write the notation that describes the distribution of the seasonal snowfall amounts. So this tells me, let me find it in here, that we have a normal distribution. So when I write my notation, it's going to have an n. We always write the mean and then the standard deviation. So in this particular example, our notation is going to look like this. It says that the average is 85 inches, and it says the standard deviation is 12 inches. So this is what our notation looks like for this distribution. Let's try one more. Example 2, the amount of time spent in traffic during rush hour from 4 to 6 in Boston is normally distributed. Let x represent the total time in minutes spent in traffic on a typical weekday during rush hour. On average, drivers in Boston spend 45 minutes in traffic with a standard deviation of 15 minutes. Write the notation that describes this distribution of traffic time. So, because this is a normal distribution, we're going to write capital N after the tilde, and then we're going to put in the mean, which is 45, and then the standard deviation, which is 15. Now let's take a look at the probability notation and how it relates to the graph. When we're looking at area to the left of a specific value, we're going to say that x is less than that value. So find the proportion of trees shorter than 81 feet in a forest where heights of the trees are normally distributed with the mean of 75 and a standard deviation of 5. So our mean is in the center, which is 75. Our mean is always in the center with the normal distribution. And it says our standard deviation is 5. So that means each time I count one standard deviation I come out, it's going to be worth 5 feet. Now, if we look at when I come out one standard deviation in either direction from 75 to 70 or 75 to 80, look at where that's at. It's right where the graph turns from concave down to concave up. So that standard deviation helps determine the shape of the graph along with the mean. Now, if we wanted to find the proportion of trees that are shorter than 81, the probability notation would look like this. We would say the probability that x is less than 81. Here's 81 and with this red line here to indicate 81. And so the probability is going to be this total area that's shaded under the graph. So all that area under the graph represents the probability that x is less than 81. So I can't stress this enough. The area under the curve represents the probability. The same idea works for the area to the right. Find the proportion of trees taller than 79 feet in a forest where the heights of the trees are normally distributed with a mean of 75 and a standard deviation of 5. If we want to find the probability of a tree being taller than 79, then that would be everything bigger than 79. So that's going to be this pink shaded area. And we would write the notation like this: the probability that x is greater than 79. When we're talking about the probability between two values, so in this case, we're talking about the probability that the height of the tree falls between 64 feet and 73 feet. So when we look at that on the graph, that's this orange shaded area. Whatever the probability is, that's going to be equal to the area under the curve between 64 and 73. Okay, last example, when we're looking at the two tails. So if I want to find the probability that a tree has a height less than 70, or remember this is the symbol for or the probability that the height of the tree is greater than 80, we would find each of the probabilities separately and then add them up. So the probability that a tree has a height greater than 80 would be equal to the area under this curve here from 80 and up. And then the probability that a tree has a height less than 70 is going to be equal to that area under the curve where it's less than 70. So this is how we want to write our notation. It's pretty much the same thing as what we've been doing earlier, but I want to stress that the area under the curve is equivalent to the probability.